Like, it's not that long ago I finished paying off the loans that I had to take to go to you. All right. Thank you for that. Let me know those things. And isn't this going to be like 40% of 1? So forth, right? All right, so here's the trick. Well, not the trick, but here's the connection with chapter 5. If they give this, not right there, we can kind of see that. If they give me the data like this, 1, 2, 3, 4. And this is why I said repeats. So what percentage of my data is 1s? 40%. 2s, 33s, 10, 4s, 20. Are you guys with me? Right? There's 2 4s out of 10, that's 20%. And now, of course, you see the connection between the math we just did, right? So the beautiful thing, if you let this happen, is that to get the mean, you multiply these and then you add them, and that's the mean. Because what's this say to do here? 0.4 times 1, 0.3 times 2, 0.1 times 3, so forth, right? Because it's doing exactly this math, and I think everybody can see where this came from. 40% of my data is 1s, plus 30% is 2s, plus. Do you guys see that? All right. So then if they give it to me like this, I just have to do x times p of x, multiply 0.4, 0.6, 0.3, 0.8, and then add, and what do you get when you add? 1 and 1.1 is 2.1, holy shit. Right? That's the mean. Of course it is. It's almost silly. It's just a reorganization of the math. Ooh, math boy. So how are we doing? Any questions you guys got? See some... Yes?
Like, why do you just put the x in front of the...
Say again?
The average. Like, what is that? The x to the x.
Well, where did this 0.4, where did this 0.6 come from?
Well, I mean,
so the label on the column tells me where these numbers came from. It came from x times p of x. Yeah. So what's the formula for the mean then for an x, p of x kind of thing? I'm trying to make a table here. What's the formula for the mean if they give it to me like this? It's the sum of, yeah, so the mean is the sum of x, p of x. Now I'm going to use population symbols. I should have used population symbol here. And you'll see why here in a minute. Now, what's the major difference between this and this? What's kind of missing here that's here? But what's at the bottom of a probability? The total number of things that could happen, which in this case is? Which is? So that's built into P of X. So they're the same damn formula. I really hope you guys see that. So it doesn't feel like you're doing the same thing because you're doing very different stuff here, but they're the same formula fundamentally. They come from the same place. So then some of you guys might be like, well, why the hell would I ever do that? I would just make a list and then I'd do it that way. So let me ask you this. Has everybody got this here? Yeah. Oh, okay. I'll take a little break. Does anybody like Dragon Ball, by the way?
Dragon Ball Z.
Did you see they have a live action a pilot of something that's going to be recurring? YouTube it. Look up Dragon Ball Z pilot.
I got the new game, it's really fun.
I haven't played a video game in so long. But the rest of you guys are like, good Lord, man. What the hell? Men never grow up. This is true. All right, so everybody got this here? So what I want you to realize is that was a very simple example. So here's a problem I'm not going to do. I just want to show you real quick how, don't even write this down. So if I saw 1, 2, 3, 4, and I saw 0.5, 0.1, 0.2, 0.2. And of course I'm being very careful to make sure that these do what? What do these have to do? Add to 1. So then you could say, well, that's 5 1s, 1 2, 2 3s, and 2 4s, and I could just make a list and do it like that. You with me? So what we're actually going to do is we're going to do this. I want you to find the mean for this situation. myself in trouble. Sorry. All right, what do I need left here? I got 0.7. Oh. I just need another 0.15. Is that right? Yeah. So if you wanted, does everybody kind of see that? That would be 5 ones, 1, 2. Do you guys see that? But this would be 295 5s, 405 6s, right? And don't do this yet. Go ahead and do this just in case somebody's going to be a smart ass. All right, that still adds up to 1, right? Just in case somebody realized you could divide by 5 and make a smaller list. Now you would need 149 eighths. 100. No, I'm not going to do that. That sucks. So look at Chapter 5's methodology. Chapter 5's method doesn't care how big this probability gets. It just multiplies them and then adds them, right? So go ahead and do that. Figure out what the mean is here. Is that 1.475? The first one. I don't know if I want to keep doing this. My brain's going to get fried. You can do it, Jeff. Is that right? Mm-hmm. And what's the last one?
1.192.
1.192?
192? Yes.
All right. All right. You guys getting that? All right. And then if you add them up, what do you get? 6.154. And that's the mean. Cool. And why does it make sense? What's the average of 5, 6, 7, 8? What's the average of these? What's the average of 5, 6, 7, 8? What's right in the middle of 5, 6, 7, 8? 6.5. Why is that lower than that? Why is the actual mean lower than what it would be if these were just the 4 numbers I was dealing with? Yeah, more of the data is down here, right? There's 70% of the data is below 6.5. So it's pulling the mean down. Do you guys see that? You can kind of make a guess as to where the mean is going to go based off of where most of the data is. All right, I like it. Some of you guys are like, well, yeah. So what is missing based off of what we said we wanted to find every time we had data given to us? What do we always want to find? We always want to find the mean. Oh, and there's that. All right. So, all right, here we go. I'm going to do 2 things. I'm going to show you the full formula, which I like the book. I think the book still says this. There's a concept formula and then there's a calculation formula. And the calculation formula is what we're going to use because it's easier to use. The concept is like too much shit going on. So let me do the concept over here by itself, and then we'll do the actual thing here. So to find the standard deviation, I always have to find what first. I mean, what's the heart of the standard deviation? Z-scores use standard deviations. To calculate a standard deviation, it's fundamentally a what? Average distance. So I've got to find the distance between the data points and the mean, right? X minus X bar. I still have to do that here. And then square it, right? All right, how are we doing? The difference is, and hopefully you see this this analogy, I can't find the mean directly from here. I had to multiply by what's often called the weight, right? The heaviest thing here is 6s, right? 41% almost was 6. That's the heaviest thing. That's the weight of 6. I've got to multiply by the weight and then do something with that. So once I get this, which is the heart of any standard deviation, I have to multiply by the weight. How we doing? And then normally you would add it up and then divide by n for a population. But again, what's on the bottom of the probability? Total number, n. N is on the bottom. So all you got to do then is add these up. Whew. And then take the square root. All right. That is disgusting. But this is called the concept form of the formula because I can see the heart of a standard deviation. And the heart of a standard deviation is the distance between data points and the mean. And I can see it. What I'm about to do is completely destroy that. I'm going to use some algebra. Oh shit. Very little algebra in here doesn't mean no algebra. It means very little algebra. So here comes. Stay with me. There's nothing you're going to have to do. We're going to make the formula and they can use the formula. All right? But when you see something like this in algebra class, what do you think? What do you do? Shit. No. Right? So let's just work on this. So you're telling me if I said simplify this, you would do like that and say, I don't like squares. Foil, yeah, good. Foil. So let's kind of break this thing down. So if I got this, in fact, don't even write this down if you don't want to. You would FOIL this out. So what would you get if you FOIL that out? Yeah, x squared minus 2 of these, right? Plus x bar squared. Right? Now, that's basically the only step I'm going to do. This is not summation algebra class. Believe it or not, you could have a full semester of summation algebra. Some of you guys know what I'm talking about. There's you're like, I don't want to know what you're talking about. So we're not going to take this all the way through. Sometimes I make that an extra credit. But can you at least see where the first term, here's what it actually ends up being. That is the variance formula. Believe it or not, it's an easier formula than that. You guys don't believe me, and I really don't care, because it's true. But can you see where this first term came from? Yeah, it's just distributing the p of x in, right? Now somehow, all this other shit becomes this. And I went back to using x bar. That's my bad. Hopefully you guys forgive me. Should be a little mu there.
Is that minus the mean squared?
But it doesn't make any big difference.
Wait, are you saying minus the mean squared? Or what is
Yep.
it? Right.
Cool. And that's outside of the sum, right? It's the sum of x squared p of x minus the mean squared. And the biggest mistake people make is they forget to square the poor little mean dude. Right. All right. So now let me show you why that's an easier formula. And of course, to find the standard deviation, you would just take square root. So you do that after you do that. So here's why that's an easier formula. Let me put that formula up here so I can work with this stuff. Okay. Here's why. This is nice. I have to do this column to figure out the mean anyway, right? Let me see if you guys can get this. I don't need any more columns. What does this formula need to sum up? It needs to sum these. So what's this missing to become x squared p of x? Do I square this? No, because that would be x squared p squared. I don't want x squared p squared. Doesn't sound good. So what is this missing to become x squared? Another x. So if I multiply list 1, just to get you to realize you're going to be doing a lot of this on your calculator. If I multiply that by that, I'll get x squared p of x. So if I do 5 times 1.475, somebody help me out. We won't stand here and wait for Jeff to do it.
7.375.
All right, sounds right. And then 6 times 2.43. Do you guys see this? You have to, when you're doing these tables, you have to realize the titles of the columns are actually little equations. So if I want x squared p of x, I just go, how do I create it? I could make a whole another column of x squares and multiply. Why would I do that shit when I just really need one more x on this dude? This times this is x squared p of x. So this times this times this is what? That makes more sense. And then 7 times this? 399? Okay. And then 8 times this? Who's it? 9.536. Do you guys understand? You could do list 1, list 2. L3 would be L1 times L2. L4 would be L1 times L3. On Monday, I'll actually have a handout that's got all of that splayed out on it. Okay. Just today, I didn't want to print it out for some reason. And what do you get when you add those? 38.7? 38.89. And that is the sum of x squared pu x. Well, I thought it was way later than it was. You should be used to this now from standard deviation. So I told you never have to use a table again to find standard deviation like that. I didn't say you never have to use tables again. And you know, that's a teacher thing to say. It's too bad. But now to use the formula, I just plug what I got. So mean is the sum of x cubed x squared minus the mean, not the mean, just the variance. So what's this here? What goes there? 38.89. Cool. You don't plug stuff in here, right? Doesn't make any sense. I get all these, add them up, and put that number there. And of course, minus the mean, which we already know was. And that'll be the variance, whatever that business is there. Yes, ma'am.
So that equation at the very top in the middle, that's supposed to be the variance?
Oh, yeah, thank you. I don't know why I started putting. So that's the variance formula. It would be really weird for the mean to equal something with the mean. Yeah. Well, here you actually shouldn't round at all, to be honest. You do that and you can kind of round out your answer, and then you take the square root of that in your calculator. You don't round until you get to the very end. So here, just tell me what's on the screen, and then take the square root of what's on your screen. So what do you get here for the variance? Blah, blah, blah. And then when you take the square root of that whole thing, what do you get? 1 point. All right, that's fine. Cool. Does that agree with everybody else, or okay? And why does that make sense? If you look at this, do the data get very far apart? If you really think about it, this would be 295 5s, 405 6s. So they're all very close to, not 6.5, they're all very close to 6.154, right? So the data doesn't get very far away, so it makes sense that the standard deviation would be on the order of 1. They don't get very far away on average. Maybe. And then I could just start asking questions like this. I could ask a question like, this is 1. 2. What percentage of the data is within 1 standard deviation of the mean?
95.
Do we know that this is normal? If you had to guess, would you say this is normal? It went up a little bit and then down and stayed about even. I'd say maybe really loosely normal, but strictly no. I can't use the empirical rule here, can I? I don't want you to. I want you to actually go calculate it. You've done this problem before. We're going to continue to do this problem several more times. Every time we learn a new way of having data presented, we're going to do this again. It's like, oh, God. So how do I do this problem? In the middle, I put the mean. It's crazy. And then I go up 1 standard deviation, so I end up at 7.163, right? Just add 1.009. If I go down 1 step, I end up at 5.145. Is everybody with me on that? We've done this before. I just added 1.009 because that's what a standard deviation is. Now here's where you got to be careful. What percentage of the data is in there then? Which data points would I include? Would I include 5? No. 6? Hell yeah. 6 is in there. There's 6. 7? Yes. 8? No. 6 and 7. So is that 2 out of 4? No. What percentage of my data is 6? So what's the total percentage in here? 6 is 40.5%. Plus 7 is,
1.
right in the same format, Jeff, 15.1%. So then you get a total of
60.1.
55.6%. If it wanted to be normal, if I was checking to see if this is normal, is that close enough to what it's supposed to be? What's it supposed to be? 68%, and that's not 68%. It doesn't look like it's very normal. Do you guys see the difference? When I gave you a list of data, you had to count and then divide by the total. We already have percentages made for us. There's not 4 data points up here. There's freaking thousands possibly, right? 295 fives and so forth. All right, maybe. So let me give you an entire problem to do on your own, and then we'll head out. And if you want to, you can use your calculator. I brought some calculators, so if you want to use a calculator. All right, what do I have here so far? 10, 20, 9, 36, 65, 65. You can do it, Jeff. All right, tell me. So one question I could ask is, verify. Hello, that was me. This is a valid probability distribution. What do you think it takes to be a valid probability distribution? Adds up to 1. Good. There's also a second thing. All the probabilities have to be between. What do probabilities always have to be in between? What's the highest the probability can be? 100% or 1. And what's the lowest it could be? 0. Good. So to answer this question, you have to show 2 things. That the sum of the probabilities is 1. Is that true? Okay, good. I was desperately trying to make that work. And secondly, that all the probabilities are between 1 and 0. Because you can imagine, you can have 4 of these added to be 1.7, and the last one has a probability of negative 0.7. Then they add up to be 1, don't they? But that negative 70% chance is weird. What the hell does that mean? Black hole of probability, right? All right, so step 2 here is find the mean and the standard deviation. And step 3 is what percent within 1 standard deviation of the mean. So the same thing we just did over there. Call me over if you need some help.